10.1, we're looking at trigonometric equations. Here's my equation. Sine of an unknown angle is equal to the square root of 3 on 2. Hopefully you'll recognise that this fraction is going to involve some exact values. So if I take a look at this triangle, notice that my angles are in radians. My side lengths involve that fraction. So sine x equals the square root of 3 on 2. I want to strip this back to get an answer for x. So what I do is take inverse sine of both sides. So if I take inverse sine of x, that will give me x. And I need to evaluate what inverse sine of the square root of 3 on 2 is as well. Now obviously I could use my CAS to work that out, but we can use this triangle. And you need to be able to use this triangle because it's very typical kind of exam 1 question. So if I take the perspective of an angle of pi on 3, then my opposite is the square root of 3 and my hypotenuse is 2. So what I'm able to work out is that x, the unknown angle, is pi on 3, opposite over hypotenuse, because we've got sine of that unknown angle is the square root of 3 on 2. So clearly that angle is pi on 3. Now that is the solution that satisfies just the first quadrant of the unit circle. So as an example, if I were to evaluate that on my CAS, I go menu, algebra, solve, and then I want the sine function, and it's sine of x equals the fraction square root of 3 on 2. And I want to solve for x. So in my settings I'm in radians, and you'll see I come up with that. And that looks pretty crazy, but I'll explain that a little bit later on. So as I said to you, it's just one solution. If we now go into our interactive, what I've really found here is if I move my point starting at angle 0 to the angle pi on 3, then you can see my x and y values. Remember, cosine of the angle is the x and sine of the angle is the y value. You can see that sine theta is equal to the square root of 3 on 2 here. So this is the solution that satisfies just the first quadrant. But if I keep on moving that point around, you can see it's also satisfied over here. Oh, whoops, not there. Sorry, here. So you can see that if I move around 2 pi on 3 for my angle, then you can see I achieve sine of that angle equaling the square root of 3 on 2 as well. So here we've got two solutions. And if I keep on moving about, I get a similar solution here, but it's the negative. And then I'll move again, negative square root of 3 on 2, so that doesn't satisfy it. But I'm back to 2 pi, and if I continue on, then you can see when I've got 2 pi plus pi on 3, it satisfies the equation. And when I've got 2 pi plus 2 pi on 3, it also satisfies the equation. And obviously I can just keep on spinning around the unit circle, multiples of 2 pi, to get solutions which satisfy it. So 4 pi plus pi on 3, and then I could move across to over here again, spin around, go back to there, continue on. And so you can see quite clearly there's an infinite number of solutions which satisfy the equation. Now just in the same way I've gone forwards, I can also go backwards. So if I just rotate this back, I'm back to 0. And if I rotate around and get to this position here, so that's minus 4 pi on 3, then it satisfies the equation. Minus 5 pi on 3 satisfies the equation. And we can continue on. So you can see there's an infinite number of solutions. Here we have our sine graph. And if we evaluate what the square root of 3 on 2 is, we get 0.86, which is roughly about there. So if you can imagine a line drawn through, then you can see that there are an infinite number of solutions which satisfy the equation because the sine graph goes on indefinitely. So getting back to my CAS, if I want to work out some solutions that made sense to me, then what I can do is put on a domain restriction. So I'm just going to go Control C and copy that. Control V. And if we put on a domain restriction, so we've got that sign of that, comma X, and then we'll say given that, we are between 0 so we've got X being less than, sorry, X being greater than that, greater than 0, X being less than 2 pi, so 2 times, and then I put in my pi function, so just here, then hit enter. You can see now I'm solving for this given that this restriction is in place, that X is between 0 and 2 pi. And now you see there are two solutions. So we've limited the solution, so it's through one revolution of the unit circle. And if we go back to our interactive, we know that that makes sense. So let's start back at 0. Because if I do one revolution of the unit circle, we have pi on 3 satisfying the equation. And we also have 2 pi on 3 satisfying the equation. So that is the same as what we've got going on over here. So our solutions for one revolution forward of the unit circle are pi on 3 and 2 pi on 3. Now if we go back to these solutions, basically what we've got is 2 pi on 3 and pi on 3, but then we have adding to that multiples of 2 pi. So we've got 2 pi here, and this n3 is just a constant. So that could be anything. It could be, or any whole number in fact. So this could be a 0, a 1, a 2, a 3, a 4, a 5, a 6, a 7. All right, so there's just multiples of 2 pi that we're adding on to it. And they could be negative values as well. So -1, -2, -3. So we're going backwards. Same story here. So it's just saying our solutions are pi on 3 and 2 pi on 3 plus or minus multiples of 2 pi. So in our notes, as we've made it really clear now, this particular solution is what satisfies it in the first quadrant. If we look at the solutions that satisfy it, if we go through forward one revolution through the unit circle, then we've got pi on 3 and 2 pi on 3. And so if we look at the solutions that are possible, then we start with pi on 3 and 2 pi on 3, and then we add to it multiples of 2 pi. So I'm adding 2 pi, 2 pi. Then I've got pi on 3 plus 4 pi, 2 pi on 3 plus 4 pi, and then that can continue on indefinitely. But I can also go backwards as well. So here I've got 2 pi on 3 minus 2 pi, pi on 3 minus 2 pi, 2 pi on 3 minus 4 pi, pi on 3 minus 4 pi, and that can go on indefinitely that direction. My next line of workings, I've just made sure that we've got it all over the same denominator, and so obviously I've chosen 3's here, and then I've combined them. So my solutions that satisfy the equation, I begin with pi on 3, 2 pi on 3, then I keep on adding multiples of 2 pi to it to get the solutions, and I'll go backwards as well. And the dots show that there are infinite numbers of solutions because there's been no domain restriction. Whereas with my CAS calculator, when I put the domain restriction that X must be between 0 and 2 pi, then there are only two solutions which satisfy the equation. So here all I'm showing is this same graph. And so if we have that sine graph that goes on indefinitely in either direction, and then I also plot y equaling 0.86, which is approximately equal to square root of 3 on 2, then you can see that we've got solutions which are here and here when we do one full cycle of the unit circle. So if I start there at the position 0, 0, I come up, come back down, and then finish. So for every cycle, you can see that there are two solutions which satisfy the equation. And then I can continue on, another two that satisfy. Same thing when we go backwards. So that's shown graphically of the intersection between the sine graph and the line y equaling the square root of 3 on 2. Now, whenever we're solving trigonometric equations, and these set of steps will become really clear when you do the first problem or few problems, First thing you need to do is find the equivalent first quadrant angle theta that satisfies the equation. So we did that and we found out that that first equivalent angle was pi on 3. We then need to determine which quadrants the solutions need to lie, taking into the signs into account. So obviously for sine, we wanted the quadrants where sine was positive, and they were the only ones that were going to work. So if we go back, in fact, what I will show you over here is that we've got the 4 quadrants, quadrant 1, 2, 3, and 4. All schools teach crap. So sine is only positive in quadrants 1 and quadrant 2. So that's what we're interested in, not 3 and 4. So if we did sine of the angles in here, then they produce positive values. Sine of angles in these quadrants produced negative values. We wanted positive square root of 3 on 2. Find the initial solutions for the valid quadrants. That is the solutions that are between 0 and 2 pi. So 1 full revolution of the unit circle going forwards. So that's the rules that we use. So remember, in quadrant 1 it's just theta, and in quadrant 2 the quadrant 2 angle will equal pi minus theta. So pi minus pi on 3, so that we worked out that this angle here was pi on 3. So how did we work out what this angle is all the way around to there? It's going to be pi minus pi on 3, and then of course pi is 3 pi on 3, so it's 3 pi on 3 minus pi on 3 to give me 2 pi on 3. So this is pi on 3, and then if we go from there all the way around to there, it's 2 pi on 3. Then we extend the list of possible solutions by adding and subtracting multiples of 2 pi, and that's basically what I've done just here. So I've said, okay, my 2 solutions which satisfy the equation in 1 forward revolution of the unit circle are these 2. I've added multiples of 2 pi, and I've subtracted multiples of 2 pi. So I've extended the list, and then I only accept those that are within the specified domain. So if there's a domain that's been given, then I only accept those and I get rid of everything else. So let's look at this. Find all solutions to the equation the square root of 2 cos of x plus 1 equals 0. This is the information I need. So quite often you need to have all schools teach crap and the quadrant angles there ready for you to use, and you need to have your exact value triangles as well. And you can see in the question that we've got a domain restriction that we're only accepting solutions between 0 and 2 pi. So I begin by writing out the equation. Notice that x is between 0 and 2 pi. In this line of workings, I've subtracted 1 from both sides, and then in the next line, I've divided both sides by the square root of 2. So cos of an unknown angle needs to equal negative 1 over the square root of 2. In our next move, we need to work out an equivalent angle in quadrant 1. So even though this is a negative, I ignore that. So I'm really looking for trying to work out what cos theta, when cos theta is equal to 1 over the square root of 2. So what's this theta? What's the angle that when we throw it into cos will give us 1 over the square root of 2? So you can see it's slightly different. We ignore the sign here. We work out that theta is going to be inverse cos of 1 over the square root of 2. So if we go to our special angles, we're looking at cos. So if we take the perspective of pi on 4, then the adjacent, because it's cos, over the hypotenuse. So we have 1 over the square root of 2. So cos of pi on 4 is equal to 1 over the square root of 2. Therefore, our theta is pi on 4. So we worked out that theta is pi on 4. That's the equivalent angle in quadrant 1. This is not a solution because what we're after is the angle so that we get negative 1 over the square root of 2. We now consider the sign. We want to know where cosine is negative. And it's negative in quadrants 2 and 3. All schools teach crap. So in quadrant 1 it's positive. In quadrant 2 it's negative, in quadrant 3 it's negative, and in quadrant 4 it's positive. So quadrants 2 and 4, negative. Our quadrant 2 angle, this is from this information, so we're in quadrant 2. The quadrant 2 angle will equal pi minus theta. So that's where we have that. The quadrant 3 angle, so here we are in quadrant 3, will start from pi and will rotate through another theta. So the quadrant 3 angle is pi plus theta. And that's shown here. We've already worked out that theta, the equivalent angle in the first quadrant, is pi on 4. So for the quadrant 2 angle, it becomes pi minus pi on 4. Think of pi as being 4 pi on 4. So it's 4 pi on 4 minus pi on 4 to give us 3 pi on 4. The quadrant 3 angle, 4 pi on 4 plus pi on 4 to give us 5 pi on 4. So these are the solutions for one forward revolution of the unit circle. So now it's time to solve for x. So we write down the solutions for one forward revolution of the unit circle, and if need be, we can add multiples of 2 pi to it and subtract multiples of 2 pi. But for us in this particular question, it's pretty clear that because of this domain restriction, I don't need to do that. So these are my solutions which satisfy the equation that was originally given at the beginning. Okay, looking at problem 2. Solve the equation square root of 3 tan of 2x take away 1 equaling 0 over the domain that we're going from negative pi to pi, including those values. Again, we need that bit of information about the unit circle, and in this case we need this exact value triangle. I begin by setting up the equation. So square root of 3 tan of 2x take away 1 equals 0. I add 1 to both sides, and now divide both sides by the square root of 3. I now think of this as being tan of an unknown angle equaling 1 over the square root of 3. I'll deal with the 2x at the very end. So let's work out what the equivalent angle is in the first quadrant. So tan of an unknown angle equals 1 over the square root of 3. What is that unknown angle? I take inverse tan of both sides, and then using the exact value triangle here, I'm able to work out that what we're looking at here is pi on 6. So tan of pi on 6 will be equal to opposite over adjacent. So we've got pi on 6. Notice that we want this to be a positive value, so we need to understand where tan is positive. So tan is positive in quadrants 1 and 3. All schools teach crap. Our quadrant 1 angle is simply just theta, so it's pi on 6. Our quadrant 3 angle is pi plus theta, so it's pi plus pi on 6, which is 7 pi on 6. We now need to solve for x. What we have are solutions, or some of the solutions, for 2x. Now the domain for x is so that it's between negative pi and positive pi. That should be a positive pi there. So negative pi and positive pi. If we are looking for solutions for 2x, then what we need to do, because the x has been doubled, we need to double the lower value and the higher value. So instead of being between negative pi and positive pi, we have solutions for 2x being between negative 2 pi and 2 pi. So these are the solutions for 2x. Here are the solutions, our first two given. And then what I need to do is add multiples of 2 pi to it, so that I feel confident that we have enough solutions to take care of the fact that the solutions overall need to be between negative 2 pi and 2 pi. And the same idea here, we go backwards and subtract multiples of 2 pi. In this line of workings, and just feel free to pause at any stage so you can digest what's going on, but basically each of these fractions have been rewritten so that they're all over 6. I then combine the fractions. And now I've limited the solutions so that they're within the appropriate domain. That is that between negative 2 pi and 2 pi for 2x. Now the easiest way, because these are all over 6, is to realise that that is negative 12 pi on 6, and this is positive 12 pi on 6. So that there is too small, that's valid, that's valid, that's valid, that's valid, and here that's a little bit over what we want, that's a little bit over 2 pi, because 2 pi is 12 pi on 6. So these are the valid solutions. And they are the solutions for 2x. We want it to be just x. So now what we need to do is strip it back to being just x on the left-hand side. So we need to divide everything by 2, or in other words, multiply everything by half. So you can see I'm doing that through here. And so now we have solutions, negative 11 pi on 12, negative 5 pi on 12, pi on 12, and 7 pi on 12 for the domain that x is between negative pi and pi. So the big trick here is just to realise that whilst your domain for x is between negative pi and pi, what we're dealing with here is 2x. So therefore you need to think of the solutions that are between negative 2 pi and 2 pi. Just simply multiply the endpoints by 2. And of course if we had solutions for 3x, then we'd multiply the endpoints there by 3. So those are our valid solutions. 3, we need to work out the general solution for the square root of 2 times sine of x, take away 1 equaling 0. So we'll ignore this general solution part and just deal with the equation in our usual way. So you can see in this line of workings I've added 1 to both sides, then I've divided both sides by the square root of 2. So we've got sine of x equaling 1 over the square root of 2. Using my exact value triangles, I'm able to work out that sine of pi on 4 is equal to 1 over the square root of 2. So inverse sine of 1 over the square root of 2 is equal to pi on 4. So my unknown angle is pi on 4. So the equivalent angle in quadrant 1 is pi on 4. I now look at solutions that satisfy the equation for one forward revolution of the unit circle. So I need to consider where sine is positive in the unit circle. It's positive in quadrants 1 and 2. All schools teach crap. So positive in all for first quadrant, and sine is positive in the second quadrant, so it's quadrants 1 and 2. Our quadrant 1 angle is just theta, and our quadrant 2 angle is pi minus theta. And that's from this information here. So in the first quadrant, my quadrant 1 angle is simply theta, and in my second quadrant, the angle swept from there to there can be written as pi minus theta. So I'm able to work out that my solutions for one forward revolution of the unit circle are pi on 4 and 3 pi on 4. Now recall, what we're actually after is the general solution. So you'll see here that there is no domain restriction, and therefore it's obvious to us that there are an infinite number of solutions, because we just keep on going around the unit circle multiple times forward and also backwards. How do we show that? Well, we're going to have pi on 4 plus multiples of 2 pi that satisfy the equation. Now those multiples of 2 pi I can write as being an unknown integer n times 2 pi. So if I want to have pi on 4 plus 4 pi, then I could write that as being 2 pi times 2, so n would be 2. If I wanted to have pi on 4 plus 12 pi, then I could write that as being pi on 4 plus 2 pi times 6, where n would be 6. So you can see there that n is just any whole number. The other solution that satisfied the equation when we did one forward revolution of the unit circle is 3 pi on 4. And I can have multiples of 2 pi added to that as well. Now here you can see I'm adding, but of course if n was a negative number, then that would be subtracting multiples of 2 pi. So the values of n that we can have are any whole numbers that are both positive and negative. So I write my general solution in this format involving the n And then I say where n is an element of z. So remember, z are our whole numbers, both positive and negative. And that's just reminding us there that n is an element of z, so these are the numbers, whole numbers. And 2 pi n is just an infinite multiples of the unit circle going forward and also backwards. This also makes our initial solution for this really clear. So the angles that satisfied sine of the angle equaling square root of 3 on 2, when we did one forward revolution of the unit circle, were pi on 3 and 2 pi on 3. And then what we're adding to it are multiples of 2 pi for that first solution and multiples of 2 pi for the second solution. So this could be rewritten as 2 pi times n, and the n3 just means it's an unknown constant, but that could be anything. So 1, 2, 3, 4, 5, 6, or -1, -2, -3, -4, -5, -6, whatever. So there's our general solution. So looking at problem 4, we've got sine of 2x equaling 1 over the square root of 2, and we've got a domain restriction so that x is an element of 0 to 2 pi, including those values. We need to solve for x. So let's start with the equation, and obviously there's no manipulation needed here. We'll deal with stripping that back to x at the very end. But our domain restriction is that x is between 0 and 2 pi. We've got 2x, so we want to multiply the 0 by 2, and that's obviously 0. We want to multiply the 2 pi by 2 to give us 4 pi. So x being between 0 and 2 pi is the same as 2x being between 0 and 4 pi. Our first job, let's work out the equivalent angle in quadrant 1. Notice I'm dealing with theta here and not x's. So sine theta equals 1 over the square root of 2. And then using my exact value triangle, I'm able to work out that that angle in the first quadrant is pi on 4. In the initial equation, the right-hand side, sine of that angle produced a positive answer. So we're interested where sine is positive. So sine is positive in quadrants 1 and 2. Just a reminder, all schools teach crap. Our quadrant 1 angle is theta, so pi on 4. Our quadrant 2 angle is pi minus theta, so 3 pi on 4. We now need to come up with solutions for x. So 2x will equal pi on 4 and 3 pi on 4. And then I take that pi on 4 and add another 2 pi to it. And I take the 3 pi on 4 and add another 2 pi to it. I can continue on like that. Remember that I just want solutions for 2x being between 0 and 4 pi, so I don't need to go negative. And obviously if it's between 0 and 4 pi, I'm not going to add multiples of 4 pi to it either. In this line of workings, I just made sure that all the fractions are written as being over 4. Here I've combined the fractions. In this line, I've only accepted the solutions which are within the appropriate domain. And in this line, I've divided everything by 2. So 2x becomes x, and then the pi on 4 is pi on 8, 3 pi on 4 is 3 pi on 8, and so on. Dividing by 2, of course, is the same thing as multiplying by a half. So whilst these solutions are between 0 and 4 pi, they're the solutions for 2x. We want the solutions for x, and so we strip it back down to what our domain that was given to us in the question. There's our solutions. So just in this section here, it's going over how we use our CAS calculator to solve for various functions. You can see I've got the equation sine of 2x equals 1 over the square root of 2, and I can find solutions for that. In my first move, just menu algebra solve, put it in, and if I just left it like this, you would understand that there are an infinite number of solutions. But I have to put in a domain restriction, so my next bit of workings here, you can see a domain restriction has been put in place so that I'm only looking at solutions where we go through one forward revolution of the unit circle, and then you can see that it ends up producing these 4 solutions. Now that kind of makes sense too, because the coefficient of x is 2. What's the effect of this 2? Well, every x value of the regular sine x graph has been multiplied by a half. So what we'll understand is that between 0 and 2 pi, we now have 2 full cycles going through, not just one. Now, usually for a trig graph, if we look at one cycle, there will be 2 solutions satisfying the equation. So if we've got 2 full cycles going through, then obviously there should be 4 solutions. So these answers here do make sense. So here we've got problem 5. It's using CAS to solve for this equation here. Notice we're involving a point 2. We're not going to be able to solve this using our exact value triangles, so we're going to have to definitely use the CAS. So the equation was -4. And we won't put the equation in straight away, will we? That'd be a silly thing to do. We're solving, so it's menu, algebra, and solve. And now the equation, -4, times it by sine of 0.2 times x. And now that is going to be equal to 3. And I'm solving for x. Hit enter, and I have this very complicated looking set of solutions here. Alright, so again, we're involving that n. And the reason for that this is a general solution. I've put no domain restriction in this equation, therefore there's an infinite number of solutions. So what I need to do is just go and take that. So I'll do a copy and go Control V to paste it. And now I'm going to put the restriction. And in the question, it's between -2 pi and 0. So just back in here, I'm going to go Control and use the given that symbol. So given that, we've got -2 times pi. We use the pi button. X is greater than that, so I just need to go Control equals and use the greater than. So x is greater than that. X is less than. So we're going from -2 pi to 0. And now if I hit enter, I have this solution. So x is -4.24031 radians is what I get for that. And there's my solution there. Usually you'd be asked to provide your solution correct to however many decimal places or significant figures or whatever it may be. Okay, so problem 6, it's a far more complicated looking equation, but we've got 3 lots of cos of 2x minus pi on 8 equaling 3 over the square root of 2. And we're looking for solutions that satisfy the domain between 0 and 2 pi for x. This is as complicated as it gets. Alright, to begin with, I write down the equation. I now divide both sides by 3 and I get 1 over the square root of 2. Notice that my angle is 2x minus pi on 8, so immediately in front of the x is a 2. So if I've got solutions for x being between 0 and 2 pi, if I'm considering the solutions for 2x, then I need to take the 0 and multiply it by 2 to get 0. And I need to take the 2 pi and multiply it by 2 to get 4 pi. So I'm now looking for solutions that satisfy 2x between 0 and 4 pi. Alright, so I've got this. Cos of this complicated expression for the angle is equal to 1 over the square root of 2. Let's work out the equivalent angle in the first quadrant. So it's not specifically of x, it's just cos of an angle equaling 1 over the square root of 2. Let's work out what that angle is. So cos theta equals 1 over the square root of 2, and using my exact value triangles, I'm easily able to work out that that angle is pi on 4. Notice that my fraction here is positive, so I'm looking, or over here, sorry, rather, is positive. So I'm looking for where cos is positive. So all schools teach crap. Cos is positive in quadrants 1 and 4. My quadrant 1 angle is theta, so that's just pi on 4. My quadrant 4 angle is 2 pi minus theta. So it's 2 pi minus pi on 4, and of course 2 pi can be written as 8 pi on 4, so it's 8 pi on 4 minus pi on 4, which is 7 pi on 4. So these are my solutions for one forward revolution of the unit circle. I'm looking at solving for x. So solving for x, well, I've actually got 2x minus pi on 8 at the moment. So my first two solutions are pi on 4, 7 pi on 4. Remember, I'm looking for solutions for 2x being between 0 and 4 pi. So I add multiples of 2 pi to that to make sure that I end up over my domain that I'm after. I'm not obviously going to be adding 4 pi to it because that will take me well over the 4 pi per area. I'm between 0 and 4 pi. I don't need to go backwards because I'm starting from 0. My next move, I write all the fractions and 2 pi's and whatnot so that they're over 4. I combine the fractions. In my next bit of workings, I'm adding pi on 8, so I want to strip it back to being just 2x, so strip it back to being x eventually, but to get it back to 2x I need to add pi on 8, the exact opposite of subtracting pi on 8. I add pi on 8 to everything, so adding pi on 8 to each of those angles here. And then I write all those fractions over 8. I combine the fractions, and I only accept the answers that are within the domain between 0 and 4 pi for 2x. So obviously if I wrote these are all over 8, so if I wrote 0, that would be just 0 pi on 8, and then 4 pi would be 4 times 8, so we're looking at 32 pi on 8. So that's why the 31 pi on 8 is within that domain. And then finally, I don't want answers for 2x, I want them for x, so I multiply everything by a half. So 2x times a half is x, and then all of these are times by a half. So these are my solutions which satisfy that equation. Alright, so problem 7, we've got solve the square root of 3 times sine of 3x minus cos of 3x, and we're looking for solutions for x between 0 and 2 pi. I start by writing out the equation. I now divide both sides by the square root of 3. And what I decide to do is try and get the sines and coses on the left-hand side. So in my next move, I divide both sides by cos of 3x. And that leaves me with my left-hand side being sine of 3x over cos of 3x. And this is one of our identities. Tan theta will equal sine theta over cos theta. So what I'm able to do is rewrite this as being tan of 3x. So my equation becomes tan of 3x equaling negative 1 over the square root of 3. So I'm looking for the equivalent angle theta in the first quadrant. So I'm not after a solution for x at this stage. I'm just saying, hey, tan of what angle will equal 1 over the square root of 3. Notice I ignore the sign. So tan of what angle will equal 1 over the square root of 3, and using our exact value triangles, we'll work out that that angle is pi on 6. Now, of course, tan of 3 of x is equal to negative blah, blah, blah. So we're trying to work out where tan is negative in the unit circle. So tan is negative in quadrants 2 and 4. The quadrant 2 angle is pi minus theta, and the quadrant 4 angle is 2 pi minus theta. So I end up with 5 pi on 6 and 11 pi on 6. Now I want to solve for x. X is between 0 and 2 pi, that's given from the question. I'm going to have, initially, solutions for 3x. So I need to multiply the 0 by 3 to get 0. And I need to multiply the 2 pi by 3 to get 6 pi. So I'm looking for solutions that satisfy 3x being between 0 and 6 pi. Here are my first two solutions, 5 pi on 6 and 11 pi on 6. So I add multiples of 2 pi to 5 pi on 6. So that gives me this and this. And now if I look at the 11 pi on 6, I need to add multiples of 2 pi to that. So that's done here and here. And I can continue on. Now the next multiple of 2 pi that I'd be adding would be adding 6 pi to it. And if I'm only after between 0 and 6 pi, then clearly that's going to be beyond what I need. In this line of workings, I express everything so it's over 6. In this line, I combine the fractions and ensure that I have the solutions between 0 and 6 pi for 3x. So these are all over 6, so the 0 is 0 pi on 6, and the 6 pi is the same thing as having 36 pi on 6. So obviously this one here is just before that end point for our domain. My next move, these are what 3x is equal to. I want to get x, so what I need to do is multiply everything in this line here by 1/3. So that will give me an x, and then these solutions. So in other words, a 6 has just been multiplied by 3. And these are my solutions for x being between 0 and 2 pi.